Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be continuing our topic of factoring polynomials, trying to determine what polynomials multiply together to give us a particularly given polynomial. And in this video, we're going to explore what's referred to as the AC method for factoring. We're going to start by exploring the problem that we last saw with the box method and compare how the AC method helps to solve that problem. We're going to identify when we go and use this technique, and of course review the process itself. So first up, let's remind ourselves of the box method. We would be given a particular trinomial to factor, and our goal was to find out what two binomials multiplied together to get us that. Well, when we would multiply the binomials, we would say that we would have these two values would multiply to give us the -2. And then we would also have these two values multiplied to give us the 12x squared. And we would also say that whatever these values produce must add up to the -5x. So we could start like before, and we could try to determine what things multiplied together to give us 12x squared. However, unlike before, we now have a coefficient in front of the x squared that's not a 1. So now the issue is we have some choice in the matter. What could go into these spots to multiply to give us a 12x? Well, we could have 12 and 1. We could have maybe 6 and 2. We could also have a 4 and a 3. Oh dear. Because when it comes to the -2, I could have -2 and +1. Or I could have +2 and -1. And what's more, not only do I have to figure out what combination of values to pick, I also have to decide what order do they go in. Because if I picked 6 and 2 and 1 and -2, let's say, then I would only be multiplying the 6 by the 1 and the 2 and the -2 together. But if I flip the order, it would be in reverse. Oh my goodness, there's all kinds of possibilities that we could have here to test this out. How are we going to decide what values multiply to give us -2 and which of those combinations add together to give us -5? Well, when I was younger, I was taught to just start testing techniques. Try 6 and 2, try 4 and 3. And then try 2 and -1 or -2 and 1 and move around the orders, right? Try to see which technique you might want to work with. That, to me, was an incredibly unsatisfactory, unelegant method for going and factoring polynomials. You mean to tell me that I have to, what's called, guess and check? I am not a fan of that. I like to have a definitive system, an algorithm that lets me know what I'm doing is correct and I'm not wasting my time. This is where the AC method comes in. The AC method is a technique for factoring trinomials where the leading coefficient is not 1. So we are going to say that we can factor a trinomial of the form ax squared plus bx plus c, okay? By the way, a, b, and c are just real numbers, okay? So those are the coefficients. So this is the situation in which we can go and actually factor down trinomials. So we have this procedure. It's a very lengthy procedure. I'm not going to lie to you, the AC method is a bit more complex of a technique to do. However, once you have it down and memorized, it's going to save you an enormous amount of time and make your work so much easier. We're going to start by taking this example here, 12x squared minus 5x minus 2. We're going to follow along this procedure step by step to see how we actually go about factoring this. Now, something to keep in mind, when we're factoring a trinomial, we need to have some notation down. I wrote here the notation ax squared, bx, and c. We should first really identify what a, b, and c are for our example. In this case, a is 12, b is -5, and c is -2. Okay? Make sure signs come along with this. That's what this form indicates here. So this notation is just the general notation for what we would call a quadratic polynomial, a degree 2 polynomial. So we know what the coefficients are. The a is the leading coefficient on x squared, b is the coefficient on just the x, and c is the constant. So with those said, we can begin our technique. I'm going to do this, I'll keep it up in blue. The first thing that we have to do besides identifying the numbers is multiply a times c. So I'm going to take a, which is 12, and I'm going to multiply that by c, which is -2. And we get -24. Okay? Our next step says, list the factors of what you got when you multiplied. So a times c is -24, so let's list the factors of -24, the numbers that multiply to get us this. Now, when I go and list factors, I try to do it in a very organized way. I start with the initial factors and then work my way up. And if it's negative, I'll make one side always negative. So like -1 and 24, -2 and 12, -3 and 8, -4 and 6. What I'll then do is I'll list the exact same factors down, except this time I'll swap the negatives. This is a nice organized way of determining what the factors are. When you're going to list factors, have an organized system in place. That's very crucial. I can't tell you how many times I see students just sit there, they look at the number like -24, they rattle off a couple of them, and then they forget a couple other factors, and then they don't list the other ones altogether. That's not going to be helpful, because what we then need to do is find which of these factors adds to give us the b term. So I need to decide which of these factors of -24 adds to give us -5. Please make sure you have an organized system so that way you can find which of these gets us -5. Sometimes students would go and they'd say, oh, right here, 8 and -3. And I say, hold on. Add those together and what do you get? They look and they say, we get +5. But our b is a -5. So what you really want are the values 3 and -8. Okay, signs are important here. Make sure you're using them. So with that chosen, we've now figured out what the factors of a times c are that add to b. And what we need to do is sub them in. So watch carefully. Instead of having 12x squared minus 5x minus 2, I'm going to substitute in a plus 3x and a minus 8x. Notice that these will simplify to get us -5x. I haven't done anything different, right? I could just combine the like terms and get right back to where I started. What I'm doing, and this is why the AC method is so clever, I have taken a trinomial that I'm attempting to factor, and I've now written it as a 4-term polynomial. When you think of a 4-term polynomial, when you hear that you need to factor one of those down, the alarm bells should be going off in your head, and you should be thinking to yourself, I need to factor by grouping. So that's the whole idea with the AC method. We do all of these initial steps to essentially factor by grouping. It's so brilliant. I absolutely love this method because once you get to the 4-term polynomial, it's pretty easy to factor. Let's pull out the GCF of the first group here. That should be a 3x, and we're left with 4x plus 1. Here, the GCF between 8 and 2 is a 2, but since the leading term is negative, I'm going to factor out a negative 2, so we're left with a 4x plus 1. So our final answer, if we factor out the 4x plus 1, we should be left with 3x minus 2. And there we go. This is our final answer. We have the 4x plus 1 and the 3x minus 2. We got our polynomial into 4 terms, and then all we have to do is factor it and write it as the product of those factors. This is going to be the central technique that we're going to use to factor down trinomials, okay? Very often, trinomials have leading terms that are not a 1. They could be almost anything else. What we have to do is find a way of breaking those down. So we have the AC method. Make sure you are comfortable with all of these steps and techniques. We're going to have to use this method again and again in courses that rely on polynomials. So really any algebra course that you're in, you're going to have to be comfortable factoring down. Even when you get to your introductory calculus courses, you're going to have to factor polynomials. So make sure you're comfortable with these techniques, you're seeing the steps, and we're really going to want to try to commit them to memory. What we're going to do now is we're going to practice this technique with a few example problems. So we're going to work through the first 2 together, and then I have a couple more practice problems I'm going to want you to try on your own. It's important to maybe color code or have very organized, neat handwriting, because with all these steps, it's very easy to make a mistake. So the first thing we should do is identify what A, B, and C are. A here is 2, B is the negative 7, C is the negative 15. So we're going to multiply A and C, and we're going to end up with negative 30. Once we multiply A and C, we have to list its factors. So what are the factors of negative 30? Negative 1 and 30, negative 2 and 15, negative 3 and 10, negative 5, and 6. Then we also have to list the other factors, where the other quantity could be negative. So 1 and negative 30, 2 and negative 15, 3 and negative 10, 5 and negative 6. These are all the factors of negative 30. And which of these do we want to work with? Well, we want to work with the factors that actually add to give us the B term of negative 7. So which of these quantities gives us negative 7 is the question. Well, hopefully you're saying the 3 and the 10, when we subtract those, we will get a 7. But which one? Do we want the negative 3 and 10 or the 3 and the negative 10? Remember, B is negative 7, so we want just 3 and negative 10, okay? Signs are important here. You have to make sure you're selecting which things add up to give you the exact B term. So that way, when we go and we rewrite this polynomial, instead of saying 2x squared minus 7x minus 15, we're actually going to say we have 2x squared plus 3x minus 10x minus 15. Again, there is no difference between these two polynomials. I could just combine those like terms and get right back to where I started. Now, sometimes students ask me, does it matter that you put the 3 there and the negative 10 there, or could you swap them? Doesn't matter. You could actually swap them, okay? That's totally fine. I just happened to write the 3x first and then the negative 10x. So, now that we have a 4-term polynomial, we can factor by grouping. Remember, I'm going to put the negative inside with the 10x. We can factor out the GCF. For the first group, the GCF is really just going to be for the variables x. So we're left with a 2x plus 3. And for the 10 and the 15, well, the GCF is 5, but since the leading term is negative, I'm going to make it a negative 5. So when I divide negative 5 from negative 10x, I'm left with 2x. Oops. 2x. And then we have negative 15 divided by negative 5 is a positive 3. Well, we have the common binomials in place, so if we factored those out, we get the 2x plus 3 times the x minus 5. And that will be our final answer. We've gone and we've taken this polynomial and we've broken it down into two binomials. Again, the central idea here is that we're doing all this pre-work to very sophisticatedly write a 4-term polynomial, because once it's 4 terms, we can get it to grouping. All right, let's try another example. Again, make sure you know what's A, what's B, and what's C. So we can multiply A and C together to get negative 15. We can list its factors, negative 1 times 15, negative 3 times 5, and then we can list the other factors of 1 and negative 15, 3 and negative 5, and we have to decide which of these is going to add to give us the B term of negative 14. Well, since it's negative 14, I want positive 1 and negative 15. Those are going to add together to get me what I need. So let's sub those in. 3x squared, and instead of negative 14, I have a minus 15x and a positive 1x minus 5. These are the exact same thing. Just combine like terms and you get right back to where you started. Well, we can go ahead and group these, where I'm going to group the first two together, and then I'm going to group the next two together. In the first group, the GCF between 3 and 15 is, well, 3. And the GCF between x and x squared is x. So we're left with an x minus 5. Take a look at this group, x minus 5. There really isn't a GCF in there, is there? There's no factors that they have in common. So I guess you could say the only factor they have in common is a 1. Well, okay. And again, we have that common binomial, x minus 5. So if we factor that out, we're left with a 3x and a 1. Here are the final factors, x minus 5 and 3x plus 1. What we're doing, as we work our way down every single step, we should be able to work our way back up. You could remultiply and distribute, and then combine like terms and get right back to where you started. So it's very easy, again, to check our work in factoring. Just remultiply, okay? Make sure every step that you do, you can always get back right to where you started. What I'd like us to do right now, take a minute, pause the video, and try to work out these two problems for yourself. I would suggest grabbing a calculator, and I would really encourage you to write your work out as I'm doing, where I list all the factors in a very organized way, so you know, for example, that you actually have all of your factors listed, and you can choose which one you want to add to the B. All right, take a couple minutes, practice this AC method, and then we'll check back in when you're done. Well, first up, I'd like us to check to make sure that we have the correct factors listed down for the AC method. Make sure you're identifying what A, B, and C are, and make sure that for each problem you figured out what A times C is, and you've gone and you've listed all of the factors for that particular value. Notice how I'm working with both positive and the negative quantities, okay? You then need to go and make sure that you're properly selecting which of these adds up to the B term. So in our case, we have B being negative 13, or positive 13, so which of these adds to positive 13? Negative 2 and 15 add up to positive 13. And then for problem 4, we have negative 25, so which of these adds up to negative 25? Hopefully you're seeing negative 4 and negative 21 do. Now that we know for certain that we have the correct factors, pause the video again and make sure that you're properly inputting these values or substituting them in for the b and factoring down from there. All right, well, hopefully you're able to get to these final solutions. For problem 3, we end up with the solution 3x minus 1 and 2x plus 5. And for number 4, I end up with 3x minus 1 and 4x minus 7. As you see how I go through the work, you can tell how I substituted the quantities in for the b term, and then how we went through and set up the grouping. Again, AC method, not that complicated of a technique. It really relies on grouping and our understanding of grouping. All that we have to do is this initial pre-work just to get to there. So if you can remember those pre-steps of how to sub things in for the b term, then you'll be good to go. Now let's change topics and let's talk about something called a prime polynomial. This is a topic that you might discover as you go and you work through different polynomials, whether it be in just a factoring unit or when we go and start using polynomials for things like rational expressions or radical expressions, etc. A prime polynomial we are going to define as a polynomial, well, that part's given. So a polynomial with factors of only 1 and itself. So a polynomial with factors of only 1 and itself. Meaning, if you try to factor this polynomial down, it won't break down anymore. The only factors it has are 1 and itself, similar to prime numbers. Remember, a prime number was a number that could only be written with factors of 1 and itself. So let's try to see how that applies to working with polynomials. Here we have a trinomial, 2x squared plus 5x plus 12. Let's factor this down using the AC method, and let's see if we can interpret our answer. So in this problem, a is 2 and c is 12. So we get 24. Let's list the factors of 24. 1 and 24, 2 and 12, 3 and 8, 4 and 6. But don't forget we could also list the negatives, negative 1 and negative 24, negative 2 and negative 12, negative 3 and negative 8, and negative 4 and negative 6. All right, well, we've gone and listed the factors of 24. We should now decide which of these adds up to 5. Well, take a look right here. 8 and 3. Oh, wait a minute. 8 plus 3 is 11. Okay, well, forget that one. Negative 8, negative 3. Oh, wait, that's negative 11. Do any of these add to 5? Well, it turns out no, none of these do. None of these work. So you might ask yourself, well, what do we do then? We would say that this polynomial is prime, meaning it cannot be factored down into any other factors. Now, I want to be careful in my phrasing here. This polynomial is prime, ... in the integers. Remember, this symbol here, the boldface Z, is the set of all integers. So what I mean by this is we cannot represent 2x squared plus 5x plus 12 as two binomials with integer values. Okay? I can't factor it down that way with integer values. There are no pairs of integers that I could plug in for these spots to make two binomials that get me this. It does not work with integers. Hopefully you're getting what I'm hinting at. I'm saying that this polynomial is prime in the integers, meaning integer values won't work, but maybe non-integer values will work. So maybe if I allowed myself to have decimals, this would work. Maybe if I allowed myself to have radicals, things like square roots that go on forever and ever and never repeat a pattern. Maybe if I allow myself to work with even larger number systems, we're going to work with values outside of the real number system, such as complex numbers. And really, in the complex number system, we can factor every polynomial down. So I don't like, or every polynomial that's nonlinear down. So I don't like really calling polynomials prime. We could say a polynomial is prime, but realize that in a larger number system, we could probably factor it down still. So for example, this polynomial could be factored down even if we go into what are called the complex number system. But that's going to be a discussion for another time. We could do a little bit easier of a problem, and let's take a look at this binomial here, x squared minus 2. Well, how would we go about factoring this down? One technique is to say, well, take a look here. Since it's a quadratic, I could write this as x squared plus 0x minus 2. This is still a quadratic. Even though it's a binomial, it's still quadratic. It's of degree 2. So I could write it in this form as a trinomial. All right, let's set up the box method because its leading term is its leading coefficient is a 1. We can set up the box method. And once we have the box set up, I'm trying to clean it up here, we can go ahead and say we need to multiply to get x squared and to get negative 2, but add here to get 0x. So what multiplies to get us x squared? X and x. What multiplies to get us negative 2, but adds to get us 0? Let's see. If this needs to multiply to get us negative 2, but whatever we put there better add to cancel out. Well, one of these things better be positive and one of these things better be negative. And it has to be the same thing. Pause the video and take a minute to think, what could we have here and here? Two values that multiply to get negative 2. They have to be the same thing if we're going to cancel out. So what could those be? Well, hopefully you're catching the trick that it could be the square root of 2 and the negative square root of 2. Watch what happens. X times root 2 is just x root 2. And then negative x and root 2 is negative x root 2. And what do you know? Those cancel out. So we could say that x squared minus 2 can factor down into x plus root 2 times x minus root 2. So it is possible to factor this polynomial down. However, it doesn't work with the integers. So we would say that this is prime in the integers, but really it is not prime in the larger number system of the real numbers. So as long as I allow for other things like decimals, irrational numbers, or even complex numbers, I can keep factoring things down. I will put a little note to ourselves. And this might not make total sense right now, but hopefully later on when we start working with complex numbers, it will. In the complex number system, every real number polynomial can be factored except for linear polynomials. There's no way linears can be factored other than one in themselves. So those are really the only true prime polynomials. So any real valued polynomial we have where the coefficients are real numbers, in the complex number system, we can factor this down. Again, we got to talk about what the complex number system is a little later, but when we start getting into things like the fundamental theorem of algebra, we'll start to see why this is. If you have any questions about the content of this video, about the AC method, or the idea of prime polynomials, please let me know. Feel free to send me an email at klinford, that's KLINFORD, at wccnet.edu. Until next time, take care.